All right, welcome to the notes on Chapter 10, Section 2. Yeah, I know we did 91293, and now we're jumping ahead to 10.2, but this is that hodgepodge unit where we're kind of jumping around. So today we're going to work on simplifying radical expressions. Okay, it's not an overly difficult concept, but it does require some number skills, and then just some basic algebra. So let's take a look. Um, Product property of square roots. So we have to understand that a radical expression contains a radical, such as a square root. Recall that the expression under the radical sign is called the radicand. This is just vocab, the radicand. Okay, and in simplest form, if the following things are true, okay, so no radicands can have a perfect square factor other than 1. We'll look at that. No radicands can contain fractions, and no radicals can appear in the denominator. So if the directions are to simplify and any of those things are true, you're not done yet. Okay. The following property can be used to simplify a fraction, and this is what we're going to use largely in this class. Is if we have the product or the square root of a times b, then we can separate them and take the square root of them separately. So here's what I mean by that. The square root of 49 is the square root of 36, also known as 6. If we separate each of those, the square root of 4 is 2, the square root of 9 is 3, and 2 times 3 is 6. So we get the same thing either way. We use that one's an easy one because it's a perfect square. We use that to do problems like this. We have the square root of 80. Now, I don't like how the book does this at all, okay? I think what the book does is they make it more complicated than they have to, so I'm going to show you a different way. So here's what I'm going to suggest. We have the square root of 80. What you need to do is you need to find the largest perfect square that is a factor of 80. Um, Perfect squares, we should just have kind of like a running list of them in our head. That's a 16, 25, 36, 49, and you know these, you can recognize them. The way to find the largest one that goes into it is we have the square root of 80. We start as big as we can and work our way backwards. So you can check these in your calculators. 80 if you need to, hopefully you don't need to. Is 80 divisible by 64? No. Is 80 divisible by 49? No. Or is it a factor? 36 is not a factor of 80, neither is 25. 16 is. So I'm going to change the square root of 80 so that it is the square root of 16 times 5. Okay, I'm just rewriting it so that it looks different. Then I can separate that. So square root of 16, square root of 5. I did that because 16, this is a perfect square. So now I can write my answer as 4 times the square root of 5. That's how I do it. I think the way the book does it with these factor trees like this, it makes a mess. I do it like this. I think it's the best way, but we'll see. We'll see if you like it. So go ahead and take a second, pause the video here, see if you can find the largest perfect square that goes into 54 and the largest perfect square that goes into 180 and simplify those. Go ahead and pause the video and do that now. All right, you're back. The largest perfect square that goes into 54 is just 9. So I would change this to 9 times 6. And that's the square root of 9, which is 3, and the 6 stays under the radical. A really nice tool to use for these problems is your calculator, but not to do the problem for you, just to check it. The square root of 54 is this ugly number here, 7.348469. If I take 3 and multiply it by the square root of 6, hold on, I got to do this differently. Let's get a better calculator up here. Let's take a look right here. So go back to, and this will be nice because we'll be able to see them at the same time. So if we have the square root of 54, that's 7.34, that number right there. And then if I take my answer and I put it in my calculator exactly the way it looks, and I hit enter, I get the same exact number. This is how I can check to see did I do it correctly. And we're not changing the values of any of these problems. We're just changing the way they look. 54, the square root of 54 and 3 times square root of 6 are the same exact number. We're just simplifying. Simplifying is, 2/4 equals 1/2. I simplified it. It's still worth the same thing. 1b, the largest perfect square that goes into 180 is 36. 36 times 5. Square root of 36 is 6. Okay. If you didn't get those, try again. If you still don't, make sure you make a note to yourself, and we can go over that in class. Multiplying square roots. We're just going to put this under one big radical. I'm going to take this, and again, what the book does, I don't like personally. So I would just change this to 2 times 14 is 28. So I put that under a radical, and then I'm doing the same thing I did in example 1. Largest perfect square that goes into 28, 4. Square root of 4, 2. And again, I can check that in my calculator the same way. Go ahead and pause the video right here. See if you can get these simplified. Go ahead and pause the video now. All right, you've unpaused. Let's take a look here. This becomes the square root of 50. The largest perfect square that goes into 50 is 25. The square root of 25 is 5. So this is 5, square root of 2. Here, this is 48. Hopefully, I'll skip a step here and we'll see how you do with it. Largest perfect square that goes into that is 16. Square root of 16 is 4, and 3 is left. Okay. Consider this expression here, square root of x squared. It may seem that x equals the square root of x squared, but when finding the principal square root of an expression containing variables, you have to be sure that the result is a non-negative. So for example, negative 3. The square root of negative 3 squared is not necessarily negative 3. All we're showing you here is that it matters. Sometimes we have to take positives and negatives into account. I'm going to tell you, don't spend too much time worried about this absolute value stuff. For our purposes, we don't need it. But it's not a bad thing to think about how positives and negatives can play out when working with square roots. Anywho, once we have variables, okay, so we do the same thing with the numbers. I'm going to take 90 and I'm going to find the largest perfect square that goes into it, which happens to be 9. Okay, and again, I don't like what the book does yet. Okay, let's do something more constructive. Let's take the bookwork and say goodbye. That's beautiful. Okay, here's what I do. I'm going to take this and I'm going to separate this into things I can take the square root of and things that I can't. So I'm going to take the 90 and I'm going to separate that into a perfect square and a non-perfect square. X cubed, I can't take the square root of an odd number. So I'm going to separate x cubed into x squared and x. X squared times x is x cubed, so it's the same value. It's just been separated in the same way that the 90 has been separated to a 9 and 10. Y to the 4th, well, that's an even exponent. I can take the square root of that. And z to the 5th is an odd exponent. So I'm going to separate that to z to the 4th and z to the 1st. That equals z to the 5th, but again, just like the 9 and 10, I've separated it. Now, here's what happens. I can take the square root of 9, I can take the square root of x squared, I can take the square root of y to the 4th, and I can take the square root of z to the 4th. Those are all going to come out of the radical. The 10, the x, and the z, I cannot take the square root of, so they're all going to stay in. So here's how I answer this. The square root of 9 is 3. The square root of x squared is x. The square root of y to the 4th is y squared. The square root of z to the 4th is z squared. What's left under there? Well, everything I underlined. 10x z. That's it. Go ahead and pause the video right here. See if you can do 3a and 3b on your own. Go ahead and pause the video now. All right, you're back from trying these. Hopefully you got something like, or well, hopefully you got exactly this. This is 4, what am I writing in white? Okay, so fixed now. 4r k squared t squared. And left under the radical is just 2t. Hopefully on 3b you got 2y to the 5th z squared, and left underneath here is 14xz. Now, I don't think those are easy, so if you didn't get those, try them again. Okay, remember you're looking for the largest perfect square that goes into each. You're separating the variables that have odd exponents. Those aren't easy problems. We're going to divide some with radicals too. The big thing here is to know that the square root of a over b is the same thing as the square root of a over the square root of b. Sounds complicated, I guess, but it makes for some easier problems. So which of these expressions is equivalent to this? Well, the way to do that, first of all, is we can divide 35 and 15, that can be simplified anyway, to 7/3. So we have the square root of 7 over the square root of 3. Okay, then what happens is we're going to multiply, we're going to do what's called rationalize the denominator. To rationalize the denominator, what we do is we multiply the denominator by some number that will get rid of the radical. In this case, it'll make the radical a perfect square. The way to make 3, or square root of 3, a perfect square is to multiply it by square root of 3. Okay, we're going to multiply it by the square root of 3 over the square root of 3 because that's 1. Okay, and we can multiply anything by a form of 1 that helps us out. So the top is going to become the square root of 21. The bottom is the square root of 3 times the square root of 3, which is the square root of 9. The square root of 9 is 3. Okay. I think rationalizing the denominator is a difficult skill. So we're going to go ahead and do number 4 together. So first I'm gonna rewrite this as 6y over 12. Okay, so I just put it all under one radical. Then I'm going to reduce this. Okay, 6 over 12 is the same thing as 1 over 2, so I can rewrite this as the square root of y over 2. All right, now I'm going to separate it again. Get this stuff out of the way. I'm going to separate it. So it's 2 radicals, square root of y over square root of 2, and then I'm going to multiply top and bottom by the bottom. Okay, it's a form of 1 that helps me. So this up top becomes the square root of 2y. The square root of 2 times the square root of 2 is the square root of 4. The square root of 4 is 2. Now I think that is a difficult concept, so I'm hoping that there's some questions tomorrow on that. Big picture is we want the bottom to be a perfect square so we can take the square root of it and get rid of the radical. All right. Sometimes we have radicals on the bottom that are rational numbers. Well, we have binomials within rationals. Okay, rationals is just fractions. So if we have a binomial, that's 2 terms on the bottom. And we're going to use what's called the conjugate to get rid of it. The conjugate is simply the same exact number, except for instead of being a plus, it's a minus. Or if this were a minus, that would be a plus. It's just the opposite. And then we're going to use what we know about FOIL to clean it up. Okay? I'm going to do these both with you because I think these are both hard also. Actually, I'll do 5a and you do 5b. So 5a, we're going to multiply by the conjugate. The conjugate here is 2 minus the square root of 2. Okay, 2 minus the square root of 2. Let's scroll up and give ourselves some room. So I'm going to multiply, let me rewrite the whole problem, 2 plus square root of 2. I'm going to multiply top and bottom by the conjugate. 2 minus square root of 2 over 2 minus square root of 2. Okay, and then I'm going to use the distributive property up top. So 3 times 2 is 6, and then 3 square root of 2. And then on the bottom, I'm going to use FOIL. 2 times 2 is 4. 2 times minus square root of 2. And then right here, I have 2 times positive square root of 2. And then positive times a negative for my last term. And square root of 2 times square root of 2 is 2. So there's that. Hopefully what you notice about this is that this is minus and this is plus of the same exact term. So they are going to add up to 0. So I don't need them as part of my answer. The numerator is 6 minus 3 square root of 2, and the bottom is 4 minus 2, which is 2, and that is my answer. You go ahead and pause the video here, see if you can get the answer to 5b. All right, you're back. Hopefully on 5b, you got 21 plus 7 square roots of 7 over 2. That is a hard problem. I'm hoping that you got it, and I'm hoping if you didn't, you try it again. If you still don't, I'm hoping there are questions on that tomorrow. Need you to try these problems for me, 1 through 16. Some of them really simple, some of them aren't. Try these, and then we will talk about them, check them in class, and that's it. I'll see you guys next time. Bye.